Hey everyone. Hi. So, just wait a second. I think everything is alright. The stream is okay, and I have the chat enabled. So, hi everyone, and welcome for this third paper session. So, we are Friday, and like I said, this is the third session. So, today we will walk and read on a published paper published in 1992, and the name of this paper is Use of Prolog for Developing a New Programming Language. And these papers have been written by Joe Armstrong, Virding, and Max Williams, the three founders of Erlang language. So, to be honest with you, I read these papers at least one time just to be sure it was not so complex, because I think we have like 17 page. That's not a small one, but we have a lot of example in Prolog, and we will try to reproduce those example in SWI Prolog. So that's why we have a little shell opened, and we will play with that. So I just want to check something, if the chat is working, and it looks great on my side. So we check the chat on different. Oh, why I can't do that? Okay, just wait a second. Okay, so it will be okay. So if you have some question, if you are on Discord, you can just ask them there. And for the others, I think I can read your comments and your messages directly from one application I just installed. So we'll see. Anyway, let's start this paper. So up, I will just zoom a little bit. Up, and it should be okay. So, this paper describes how Prolog was used for the development of a new concurrent real-time symbolic programming language called Erlang. Erlang was developed by first building a prototype in Prolog. The prototype was used by a user group to test their reaction to the language. As time passed, many features were added and removed from the interpreter, and eventually the language reached a level of maturity where it was decided to try it out on a significant problem. So, just for the context, Erlang was created, the project on Erlang started in 1986, and the first paper was published in 1989 or something like that. And so we are 3 years later, and if you want to the story, the big picture is the people working at in the laboratory were trying it and sharing this project with other teams, and so that paper will explain how to use Prolog to design something. And so 3 years after the first paper. About 3 years and some 20,000 lines of Erlang later, performance became an issue. We wrote Prolog cross compilers from Erlang to various concurrent logic programming language, followed by a direct implementation of Erlang itself. The direct implementation of Erlang was loosely based on the WAM, so WAM is for Warren Abstract Machine. That's the theory behind Erlang. So that's these things here. And so Prolog was created using this kind of machine. or not created but upgraded, we can say. And so if you're interested to read it, you have a really nice paper and a great book about this one. I think this is, don't remember the name, but you can find a lot of interesting information about this abstract machine. The idea is it's not a stock machine. It's like, again, the big picture is if you have a lot of small processes, a lot of small machine having their own stack dedicated, and so you have a lot of register and you can switch between those kind of register. It's more complex than that, but you have an idea of how it's work. Anyway, the direct implementation, blah blah blah, made by writing a Prolog compiler from Erlang to a new abstract machine and an emulator for the abstract machine in C. The instruction set for the abstract machine was first prototyped in Prolog. Finally, the compiler was rewritten in Erlang, thus totally removing all dependency on Prolog. This paper describes some of the key events which lay between the simple prototype and the current version of the language. Okay, let's try that. I will it would be easier for me to read. This paper describes the development of the Erlang programming language. Also, we did not know it at the time. We were unwittingly following the advice book, who argued that software systems should be incrementally grown rather than designed in a conventional manner, and that rapid prototyping should be used as a design methodology. So I just want to check this one and this one. So BR86 and AR90. So following philosopher problem of logic programming and using Prolog for rapid prototyping. Okay. BR86. No silver bullets. Oh, I know this one. Essence and axioms of software engineering. I will put it there because I think I already read it in the past. We'll check that later. So it was never our intention to develop a new programming language. Erlang emerged as the side effect of an attempt to find an elegant way to program a PABX for private automatic branch exchange for simple telephony application. The groundwork for this is described in GA86 and some of the conclusion of the initial programming experiments in AR86. In writing this paper, we have followed the advice of Parnas and Clement, PA86. That is, we present the development of our language as if it had been the result of a rational design process, whereas in fact the real design process is virtually impossible to describe. So PA86. Where is it? Rational design process. Oh, and why to fake it? This one, I don't know this one. Can we have it in PDF right now? Yeah, we can have it. Another one to read. Yahoo. Okay, so the success of the development is in large measure due to Prolog. Indeed, had it not been for Prolog, it is doubtful whether language such as Erlang would have emerged. Prolog provided the kind of interactive environment which could accommodate the rapid changes in direction which occur during the development process. At a finer level of detail, the implementation of Prolog provided the inspiration necessary to make an efficient version of Erlang. The errors in Prolog, things which we would have done differently, provided inspiration for how not to do certain things. Erlang supports a number of mechanisms not found in Prolog. Erlang is a concurrent, real-time, distributed, functional language suitable for building large embedded real-time systems. It has modules to support programming in the large code can be changed in a running system on the fly, and it has sophisticated error trapping mechanism which allows the construction of highly robust software systems. More details are available in AR 89 and AR 90. So I think we have read those one here. The language started as a simple meta-interpreter which added notion of concurrency and various error handling mechanisms on top of Prolog, and finished as a programming language in its own right. The ideas behind the Erlang interpreter are described in the section 2. Having built a simple interpreter for Erlang, we were keen to use it on real problems. A group of application programmers started using it for prototyping real telephony applications. Some of the results are described in PE 91. So PE 91. Oh, that's great. I think this one is not listed in my in the awesome Erlang list. Check that later. The influence of the user group on the development of the language is described in section 3. As the language developed, it obtained its own syntax and its relation to Prolog weakened. The development of the language itself is described in section 4. Up to now, the development had been highly informal. The interpreter, which was changed almost daily, was the only definition of the language. As the interpreter matured and change became less frequent, proper documentation became necessary. This change is described in section 5. After about 3 years, the user group was satisfied with the resultant language. A study was made of approximately 20,000 lines of Erlang, which implemented various features in the telecommunication switching system. These features have previously been implemented in conventional languages. Program design using Erlang required between 7 and 22 times less work. Performance of the language now becomes a primary concern. While satisfied with the expressive power of our language, our users required an implementation which was at least 40 times faster than the original interpreter. Section 6 describes our attempt to speed up the implementation of the language. The first attempt was to cross-compile Erlang to Prolog or Strand. Inspiration for the next stage in development came from the WAM. Since Erlang had grown out of Prolog, it seemed natural that the techniques used to make fast Prolog systems should also be applicable to Erlang. We describe how we made a fast implementation of Erlang. Section 7 describes the current status of the language. Section 2, First Interpreter. We start with a discussion of a simple Prolog interpreter for an extremely restricted subset of Erlang. The first interpreter was a simple Prolog meta interpreter which added the notion of a suspendable process to Prolog. This interpreter was the starting point of a series of experiments to try to find out what features should be included in a language suitable for programming robust concurrent real-time application. The first interpreter was rapidly modified and rewritten to include the functionality identified in a series of detailed studies performed to establish the desirable characteristics of a language for programming telephony application. At this stage, the entire interpreter could be rewritten in matters of days and simple extension could be made in hours. In the following sections, we describe the basic techniques used in the first interpreter. Suspending computation. The first step is to program a suspendable computation. We want to write a meta-interpreter which can be suspended at any point in time. It should be possible to resume the computation later. Okay, let's try that. So that's really great because it will be a good time and a good moment to introduce you Prolog. So this is SWI Prolog. Prolog interpreter, classical one in open source, so it should work. So to insert something like a rule or predicate, we can use the assert functions. We have the assert A and assert Z function. This one here we just put, I think, at the bottom of the rules. Here it will be at the beginning and here at the end. So the idea is we will create that. So the first element will be solve A, B, solve A, solve B. Okay. It's not good. Okay, it's better. I think this is an old version. Then we will put at the end. So we will need to have solve A. So I have a call to built in, but I think I don't have it, but we'll try that anyway. And the next one is rule A, B, solve B. Okay. Consider the vanilla interpreter solve 1, which is written as follows. The intermediate stages of the computation are inaccessible to the programmer. The goal solve 1 terminates when a solution has been obtained and it is not possible to suspend the computation while it is taking place. Let's try it. So we have that, and I want to solve, for example, X. And we don't have the building, so it can't work. But the code can be executed, and we can add it directly in the knowledge base. The simplest way to provide a suspendable computation is to keep all unsolved goals in a list, and successively take the goal at the head of the list, solve it, then solve the goals remaining in the tail of the list, together with any new goals which may have been generated in solving the goal at the head of the list. This can be achieved as follows. Reduce. Okay, we will try to create this one as well. So assert A this time. So we have a reduce. So that's a fact. Then variables. So reduce x t, so we are looping into a list. This is a recursive function, I guess. We will call x, we'll backtrack it if it's valid, and actually we will reduce it. Oh, sorry, we will backtrack if it's invalid, and if it's valid we can reduce it. I think it's something like that. And then we have the LHS and more, and we have the I don't remember what is AQN. Prolog. I don't know if its predicate is existing. It will not work, I think, because this function, this predicate doesn't exist. So I'm not sure it will be okay. That's not cool at all. I will probably create some things to fix that later. Blah 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 blah. Here. Okay. So let's try to understand this thing. We will call x. So let's try it. So I think the EQN is for maybe equation or something like that. This is weird. Let's try it. So we have the reduce. This one will return true, so it's okay because the list is empty. And there we will have a goal. For example, just put x at first, just to have an idea of what's going on. And so actually it can't work because argument is a free variable and it can be executed. So let's try to do something like, I don't know, user x, and actually user doesn't exist. What kind of predicate I can use to check that? That's a good question. Maybe I will create another session, like for example adding a user called test, just for fun. That's a fact. Okay, that's interesting. So we call x and we can reduce, and if I'm doing something like that, I don't know, what can I do? Okay, so the first one is okay because we are coming here, we are calling it, and we are reducing it after, and we will go there, and it doesn't work, and I don't know how to come here. I think it's when we have something outside the tuple, for example, something like that. Yeah, that's right. Okay, so the equation function, maybe, I don't know how to say that. We'll try to find RHS will append more one. Okay, reduce more one, and we come back there. So I think we will solve an equation here. This is the goal here, and the result of the goal will be directly put in more. And more one actually a free variable. And no, this is the output function. So we have the RHS, we have more is the will contain is the original list here, and the more one will be the result of those lists, and we will put it in the reduce, and we'll loop until we have the reduce done here. So this reduces the list of item 1 and 2, where it assumes that items contained in curly brace are Prolog goals, and that all other items are user-defined rules. As an example, we show how the well-known naive, reverse, and factorial function can be written in terms of equation 2, maybe. So we have the definition just after. So we have the definition here. That's really complex. Just for factorial, doing that is so weird. Let's try it. So I will just copy paste those links. So we will just barely put that here. So it's working. So we have the factorial. I think there is many different kind of function, and those are different goals, and because we have different name with them, it will solve different kind of problem. I'm not really an expert with Prolog because I didn't really use it a lot, so it's a bit hard to understand everything. So let's try it. So we have reduce fact 3f, for example, just this one. Oh. So why it doesn't work? Result 6 f equals 6. This code is not working. Why? Okay. So maybe this one is just working like that. Nope. Okay, so we have the list of the functions that will be called. That's every time I'm doing some Prolog, it's look like black magic, you know, because you can do a lot of stuff with only few lines of code. It's a bit hard to understand it at first glance, but when you can, it's just crazy. Oh, this one is working. So this one is working, but it's crashing. Perhaps I did something wrong. Nope. If we were to try successive iteration of ReduceOne for the factorial example, the following will be obtained. Okay, I think we can do trace. I think we can do that like that. No? So we have the list of the different execution. That's really great. And we can do the same with Factorial, I guess. Oh no, that's the one I was solving. The previous one here. Oh. So this one is working, but I think I did a mistake in the definition, so we'll see that later. If we were to, okay, so we have the same results there. So the trace function is really nice in Prolog. As you can see, we have the full list of execution that this program will generate when we try to call this goal and to when we are executing this part of the code. So the idea behind that is to have an idea of what kind of thing every predicate will produce during the execution. It's incredibly powerful, incredibly nice, and that's probably one of the best features. Not the best because we have a lot of crazy features in Prolog, but in this example, that's crazy because I don't really know a lot of programming language with this kind of features. For example, if you try to do the same with C and GDB, for example, or any kind of tracing library, you will never have something like that. It's easier to do it with a printf, for example. The list of goals which remains to be reduced at any particular point in the computation is a normal Prolog data structure, which can be manipulated in any way required by the user. In particular, we may decide to suspend the computation after a fixed amount of reduction. Suspending the computation after a fixed number of reduction. The predicate reduce3 is similar to ReduceOne, with the difference that it always terminate before a fixed number of reduction has been performed. The goal reduce, goal list, reduction, and result reduces the list of calls in goal list, binding a result to either terminated n or continuation more calls. Terminated n means that the computation completed with n reduction, continuation more calls, is returning after 20 reductions have been performed if there are still outstanding goals in the goal list. Reduction is used to count how many reductions have occurred. Okay. Wanted to try, but it doesn't work to copy everything. Not a problem. We will do it one by one, and it gives me the opportunity to read it a little bit and try to understand it. Yeah. Sorry, just missed a parenthesis. So when it's terminated and we have nothing, we can backtrack. When we have some goals remaining and we have 20 iteration, we can do continuation. And when we have items present in the list, we can call them, increment the continuation or the goals counter, and reduce the list. Okay. I start to understand how this thing is working. And here we have the same stuff. We are trying to... Okay, so if it's another kind of calls, we will call the predicate equation and put the result directly in the results and return it after, I guess. Oh, I think I did a mistake. I don't think it will work because yeah. I think it will not be available. Trace, I don't want it anymore in trace. I don't remember how to do that. No trace. Okay. And we are just in debug mode, so it's okay. Let's try this goal. Terminated 16. And we have the same result. That's crazy. So that's the result. And this is the one from the paper. This is exactly the same. This is amazing. It's awesome. It's just crazy. So for the one who are not really friendly with Prolog, you don't you know, when you are creating something in any other language, you can return something directly to a function. This is not the case in Prolog. In Prolog, you are creating three variables that will contain the final result. That means that when you are creating a predicate, and you can call it, for example, a function in this case, the variable and the goals present in these predicates, some of them will not be free variable. That means they will be bound to a constant, or you know, something that already have been instantiated directly in the interpreter. And you will have some free variable. Those variables are like this one. This one here, for example, is an inbound variable, a free variable. That means there is no value in it. If you put, for example, x equal 1, it is not a free variable anymore. This is a bounded variable to the values 1, and you can't modify it. If you try to do something with that, so for example, say x equal 2, that's false because x equal 1, and you can modify this value. This is the immutability of the variable in Prolog. And if you create something with a free variable, you will have the final result stored directly in this variable. And if you look at the rules from, for example, SWI Prolog, don't know which one, find all, for example, you will find sometime a thing just before the variable. That means this one is a template that's a variable that will be used by the function, by the predicate. The goal is, for example, a fact or something you want to look on, the predicate you created by yourself, you know, or something like that. And the bag here with the -1, with a minus symbol, will mean, it means that this predicate will return the values of the execution directly in the bag variable. So we will do some example after, but that's the idea. So we have a lot of code execution. I think it will work as well. Let's try this one here. Oh, okay. So we have practically, no, we have the same result, except the x1 here is not x1. So as you can see, we have a free variable here. It's a unbound variable. The underscore 20,830 is a free variable. That means this variable is not bound to any kind of variables or constant, sorry. But we have practically the same result. We can, of course, restart the computation represented by continuation new goals by solving a reduced goal result one later. Really? I want to try that. Let me copy past this this line now. Okay, new goals. Oh no, okay. So this is the goal there. Okay. So we have the result, and if we recall it in goals, we have we can probably execute it again, right? No? Okay, I think I need to extract this value from continuation. So we have the result here, and what we want, we have the continuation in the result, and the result will be added there, I guess. Let's just try like that. We have the continuation. Okay, we can do it in a different way. Okay, and now we can call reduce z and the result 1, for example. Result 1 equal terminated 2. But where is it? Oh, okay, the result is done. So just to make things clear, that's pattern matching. So we have the result here, but the result you know, is made of continuation facts or predicates, and in this continuation you have a list of values that need to be computed after, and we need to extract those values. And to do that, we will do some pattern matching. The pattern matching means that we will put a free variable. This one is not defined anywhere else in the code, and we will extract those values and put them in the variable, and the z variable will be put at the first argument in the reduce function, and we will reset the counter, and the final result will be stored in the result 1, just there, here. And we have the R variable containing the final value. As you can see here, this is not terminated correctly because we have a free variable, and here we have the complete list of arguments. A multi-task scheduler. The reduction mechanism in the previous section can be used as a basis of a simple round-robin scheduler, like MultiReduceOne. This takes a list of tasks of the form job and goals. The scheduler allows each job to run for at most 20 reductions. It then goes on to the next task, etc., until no more tasks remain. N is the name of the task, and goals is a goal list representing the task. Let's try the multi-reduce function. So when, missing parentheses again. So that's a fact. If we have an empty list, we just return true. Then we have the list of job, and we will try to extract them, at least the value and the goals. Then if it's terminated, we will continue the multi-reduce only if there is some remaining task. And we will, if we have some continuation, so probably because of the reduce goal, we will extract these values from the continuation and execute them and put directly in the job queue. That's really elegant. That's a really elegant way of doing stuff. That's nice, really nice. Okay, so now we have added a few write statements so we can observe what's happened. Okay, let's try that. That's crazy. You know, this paper is from like 30 years ago, maybe more, and it's just working like that on my computer with version of SWI Prolog. That's just crazy. Starting one job, yeah, and so we have the facts, and oh, we have a loop because actually I didn't stop it. So yeah, I don't remember to break like that. Okay, but it's working, as you can see. Yeah, and we can just put a dot to say stop, it's over. And we have the job 2, we have terminating, starting 3, job 3, job 1, terminating 1, and after we have the result of the computation. Here we see that the 3 goals, and rev A, B, C, D, blah blah blah, and rev and fact were executed concurrently. Can we have a proof it has been executed correct? Oh yeah, I think terminating jobs 3. Indeed, it has been executed concurrently. We don't have the same order. We have the same result, but we don't have the same order. This is a form of pseudo-concurrency since we only have one processor. The maximum number of predictions which are allowed before a task is suspended is analogous to a time slice on the process of swapping task to a context switch. Each single thread of computation is analogous to a process, an interpreter for functional style of programming. If we ignore for a moment context switching and return to the basic reduction cycle, we can define ReduceOne, which supports a more functional style of programming. Oh, this one is a little bit more complex. ReduceOne. Not sure if I will create it. I will load it somewhere, like here. quite dirty, but it should work. It's working. We have the ReduceOne. Yeah, we have ReduceOne, so it's working. That's this version of. Okay, we'll try to understand how it's working. So we have the variable called images. Okay, return value if the values is returned. ReduceOne x, write x. Okay, I don't really understand everything, but I think this is practically the same program than the one before, but we have some kind of specific fact of predicate that we can put during the execution. Not sure. Not that in on this version of our interpreter, write1 and NL0 are no primitive function in our meta language. They can be written directly, not enclosed in curly brackets, curly brace. Adding new primitive to the meta language can be easily achieved. As for write1 on NL0, returning to our Factorial and naive reverse example, this can now be written. Okay, sorry, but I will put that everything in this file here. It's quite time consuming to do everything by yourself. And this one here, let's try it. Okay. Try this one. Oh damn, it's working. That's crazy. So what's going on? We have the factorial 1, write x and NL. So ReduceOne factorial 1 of 4, write x NL. Okay, let's try this time with this function here. It's working as well. It's pretty slow, really slow, but it's still working. That's just crazy. A functional language with processes and message passing. In our final and most complex example, we combined the IDs of the previous two sections to form an interpreter, ReduceOne, which supports the functional style of programming, allows process creation and simple message passing between processes. Each process is represented by a data structure of the form job ID goals mailbox, where ID is the name of the process, goals is a list of unsolved goals representing the computation, and mailbox is a list of messages which have been sent to but not yet received by the process. The goal ReduceOne goals ID mailbox jobs represents the current state of a simple multitasking operating system. Goals ID and mailbox represents the currently executing process, and jobs a list of all suspended processes. The list of such processes we call an environment. Oh, this code is really hard. We're not doing that with our session method because it will take a while. Okay, let's try. Okay, it's working. The meta language primitive spawn ID goals schedule a new process with name ID and goal with list goals. Send ID message and the message to the process ID. Receive is the function which returns the first message in the mailbox of the process. Okay, The scheduling algorithm used in the interpreter is extremely simple. All processes proceed until they either terminate or until they try to receive a message and no message have been sent to the process. In reality, we used a more sophisticated scheduling algorithm which combined time slices together with context switching when a process could no longer proceed. Okay. The relations EQN2 define a new meta language. A simple program in terms of this meta language could be the following: go spawn sender spawn catcher. Okay, let's try that again. This creates two processes called senders and catcher. Sender sends 5 messages to catcher and then terminates. Catcher receives these messages and terminates when it receives a termination message stop. Okay, let's try it. Oh, it doesn't work. Why it doesn't work? What's the problem? Okay, one thing is missing. The EQN4 predicate does not exist. This one here. It doesn't work. I think I will need to create it. Or maybe there is no mistake here. I think this is probably a typo here. Maybe it's EQN2 and not EQN4. We'll try to correct that. So we have a typo in this paper. This line here is not a good one. So this is EQN2, not EQN4, and it generates the same output. So spawning sender, spawning catcher, terminating startup, resuming sender, pipe 5, 4, 3, 2, 1 sender catcher. That's really the same. But I will not explain the code here. This code is pretty hardcore. I don't understand everything. I need to read it, you know, in a quiet environment. But I think the idea is to recreate and isolate all process together during the execution. And we are sharing some special values like ID and so on, and we have the environment here. You know, the writers were talking about this element called environment. Okay, so let's continue. Properties of the first interpreters. The interpreters of the previous section show how we can establish a process-based model of computation in Prolog. There are many things wrong with the above interpreters. The meta-languages are user-hostile, and any mistakes in the user meta-language program will crash the interpreters in a number of bizarre ways. The interpreters are themselves ridden with appalling lack of concept for efficiency. Our actual interpreter used different lists to eliminate all appends from the program and was somewhat more efficient, though less clear, than the version we have presented. In the early stages, languages features could be implemented in a few hours. Invariably, all the discussions preceding any language change took much longer than the time taken to implement the change. During the development period, the language interpreter itself underwent a very large number of small changes and several large changes which required total rewrites. The interpreter itself proved extremely robust and highly portable. Yeah, that's true. That's very true. Even 30 years after, we can still execute the same code in a recent version of a Prolog interpreter. That's that's insane. The first version was a new Prolog version running on a VAX 11750. It was then brought to Quintus Prolog on the same machine. The user group had access to PCs, so it was ported to LS Prolog runtime, and we then ported it to Sixtus Prolog and changed from our VAX to Sun 3, and then to Sixtus Prolog running on Spark. None of the above changes of Prolog system or computer queues use more than momentary and easily solved problems. We had far more problems due to the incompatibility of operating system, especially between MS-DOS and Unix, than we ever had between the different Prolog systems. And this despite the fact the Prolog is still not a standardized language. Oh, that's crazy, because at this time Prolog was not a standard. Using the techniques described in section 2.1 and 2.5 and the syntax described in the section 4.1, we wrote the first usable interpreter for concurrent language. This language had the following characteristics: concurrent processes, selective message spacing, process groups, error signaling and trapping mechanism based on process group, inline Prolog code, time slices, round-robin scheduling, tracing interprocess messages, debugging individual processes, I/O to virtual channels, ports, all of which took approximately 1,100 lines of Prolog code. The first interpreter was then used to experiment with different language construct, scheduling mechanisms, programming styles, etc., aimed at finding a convenient and elegant way of solving simple telephony programming problems. For this experiment, we used an Ericsson MD110 PABX, blah blah blah, which we controlled from our Prolog interpreter. After a period of experimentation, during which we made rapid, almost daily changes to the interpreter, meta-language and programs in the meta-language, a style of programming and version of the interpreter emerged, which we felt was good enough to be used in a wider context. User group. Once the first interpreter had stabilized, a user group was formed. This was a group of application programmers outside the computer science laboratory who were interested in experimenting with new architectures and ways of programming a small PABX. The formation of the user group forced a measure of stability on the development process. CSL members were obliged to deliver their ideas according to a time schedule and produce working and documented version of the software. For over a year, CSL and user group members met once or twice a week. in an attempt to understand each other's problems. This process was invaluable. The users, with their long experience of application programming, suggested many valuable changes to the language, which were easily incorporated in the interpreter. CSL members were able to convince the application programmers why certain imperative styles of programming led to problems and should consequently be avoided. This process, while at times somewhat frustrating, was in retrospect one of the key factors which led to the subsequent acceptance of the language. It is interesting to note that once the user group started using the language started changing again, despite the fact that the language had converged prior to releasing it. It appears that the language converged twice, firstly to fulfill the internal need of the CSL developers, and secondly as feedback was obtained from the users. Development of the language, syntactic development. We take naive, reverse, and factorial as example. The syntax used in section 2.4 was: by defining the infix operator arrow, we can write this as valid Prolog data structure and omit the functor simple equation 1. I'm not sure if this is a valid syntax for Prologs right now. Don't know. We'll see that right now. No, it doesn't work. I think this operator needs to be defined, I guess. Yeah. The above syntax was the first syntax which real users were subject to. The disadvantage of this syntax is that error messages, runtime diagnostic, are in terms of Prolog data structure, not Erlang. After the language had been in use for about a year and reached relative stability, we wrote a parser for Erlang which gave the language a syntax of its own and allowed us to invent syntaxes and structures which were not valid Prolog in the new syntax. Okay, after a short time with the new syntax, we adapted a purely functional notation which avoided the need for superfluous temporary variable in this current syntax we now write. Concaten ref t. Okay. So this code is working in Erlang. Definitely this code will work in Erlang. Let's try it. But I can assure you this code will work. No, I don't want to do that. Okay, let's try it. I think there is a mistake somewhere, perhaps on my side. Concat th. This is good. Okay, concat is undefined, so I think we can use list concat. Yeah, that's just. So just to show you that code from the past, like 30 years ago, is just running like that without any kind of big modification, just because at this time the concat function was present directly in the built-in function, and now the concat is available from the list module. But this is the only modification I did, and it's working. It's just crazy. The effort involved for each of these syntaxes can be seen from the following: original Prolog clauses, zero line of Prolog code, infix operator, arrow plus code to read and convert erlang function to a normalized form, 91 line of Prolog code, parser in Prolog, a bit more than 1000 line of Prologs. Crazy. The parser was first written as a Prolog DCG, but the idea of using a DCG was rapidly discarded due to the problem concerned with providing meaningful and precise error diagnostics. This is why we don't have DCG in Erlang by default. So for the one who don't know, DCG is a kind of parser system. I prefer this way of parsing stuff than using, for example, Lex or Yak, and you are defining a kind of rules, and those rules are following a tree-like environment. So when you put a string, or I don't know, something that could be easily parsed by the code, this program, this application will read each terms in each part of the string in different matters depending of the value you will find. So for example, you can parse the digits, and these digits will be stored in different way, and then you will have the separator, and the separator, for example, a dot and then a space, and you will create all the program and all the tokens directly by using this kind of DCG grammar rules. That's really awesome. But that's really interesting, because when I started to use Erlang a few months or years after, I started also to use Prolog, and I liked the idea of DCG, and I was a bit frustrated to not have it directly in Erlang, and instead having like Lex and Yak, you know, the two tools to create parser in Erlang, greatly inspired from I don't remember the name. I think it's also Yak and Lex from GNU Toolbox. But that's the idea. The parser, okay. So because we don't have enough error diagnostics, crazy. The solution to this was to completely flatten Erlang grammar into an left parser, I guess, an LL1. It's left parser, I guess. I don't remember, because we have right, left to right. Okay, see, it's a left to right parser. It's a top-down parser for threading. Okay. On right, a conventional recursive descent parser for the language. At the time, we remove the possibility for users to define their own infix operator. Language changes suggested by the new syntax. Moving to a fully parsed version of the language suggested the introduction of the following features: tuples, write in curly brace, item 1, 2, etc., for storing fixed number of items, function with zero arity are not funct, whereas atoms with the same name have no parentheses. I think we can share this sentence with the guys from Elixir. A module system function guards. Changing from a Prolog to a new syntax had more than a cosmetic effect. Because it was no longer Prolog, we were forced to think more in terms of the meaning of a language construct, rather than to just rely on the meaning of the statement when it was translated into the equivalent Prolog. Often, the semantics of an Erlang expression were not the result of a conscious design decision, but were the accidental result of the implementation in Prolog. We call this phenomena semantic embedding. The semantic of Prolog became accidentally embedded in Erlang. We first became aware of this phenomena when we wrote the Erlang parser. At a later stage, when writing the compiler, we were forced to completely remove any remaining dependencies upon Prolog. As an example, consider the Erlang expression. In the interpreter, this was translated to the Prolog. Oh yeah, that's... wow. So the meaning of an arithmetic expression in Erlang was defined to be the meaning of whatever the corresponding expression was in Prolog. When we wrote a parser for Erlang, we had to define a grammar for arithmetic expression. Defining the grammar process forced us to think about if we wanted to follow the Prolog grammar for arithmetic expressions or use some other grammar. Another accidental consequence of the interpreter being written in Prolog was that in the original version of Erlang, all variables in Erlang were represented as Prolog logical variables. Eventually, we decide that logical variables as in Prolog had certain undesirable properties in Erlang. This was because sending a message containing the logical variables between two processes allows the processes to communicate by an invisible mechanism, binding the variable, and not by message passing. We wanted all acts of inter-process communication to be explicitly achieved through message passing. Defining documents. Erlang first appeared as a simple Prolog meta-interpreter. At any particular point in time, the interpreter was a language definition. The language itself had no defining documents and was defined totally in the terms of its interpreter. Eventually, we started writing manuals, reference guides, etc., which described the language. Since the language was undergoing rapid change, the interpreter and the manuals were often out of phase. In the early stages of development, if the interpreter and the manual differed, then the interpreter was correct and the manual wrong. This allowed users to answer any question about the language by try it and see. As the language matured, we came to a point where this approach had outlived its usefulness. We then reversed our policy. If the language and manual differed, then it was the manual which was correct and the implementation which was wrong. Okay. At this stage, we took a lot of care to ensure that the manual was correct. This is very difficult. While the Prolog system provides very careful proofreading of the interpreter, no such help could be found to help get the manual right. This is exactly the opposite of what is supposed to be conventional practice. One is supposed to write the defining document first and then make the implementation. Our way is much easier. It is easier to describe something which exists than to imagine the properties of something which does not exist yet. The shift is emphasizing from the interpreter to the manual of the defining document reflected the achievement of a new level of maturity in the language. Performance. The decision to concentrate on performance represented a milestone in the development. We had now entered a period where we were only interested in the performance of the language. We could leave the semantics in change while concentrating on implementation. Our first idea was to cross-compile Erlang to a concurrent logic programming language. This seemed natural since all our effort has been directed towards adding a notion of concurrency to Prolog, and in a concurrential logic programming language, concurrency is free. We then made implementation loosely based on the WAM on its descendants. Cross-compilation to concurrent logic programming languages. Our first attempt were to write cross-compiler in Prolog from Erlang to Prolog on Strand. Of this, the resulting Strand-based implementation was an order of magnitude faster than the Prolog interpreter, but still not fast enough to meet our requirements. The cross-compilation process, which is described in detail in chapter 13 of A489, turned all Erlang function of ReduceOne into Strand goals of ReduceOne plus 8. The resulting program did not, however, achieve the kind of performance we required. We encountered certain problems in compilation to language like Strand. Our models of concurrency were different. Erlang provides concurrency at the process level. Strand has much finer grained concurrency. Our strategy for error handling was different. There's an other problem forced use to think in terms of our own implementation. Compiler to a WAM-like machine. The context stage of development was concerned with building a high-performance Erlang machine. The Strand on Prolog implementation neatly sidestepped several nasty implementation issues: boon time garbage collection, real-time scheduling, and so on. The first compiled version forced use to think about such issues. Inspiration from the compiled version of Prolog came from the WAM. Since Erlang had grown out of Prolog, it seemed natural that the techniques used to make fast Prolog systems should also be applicable to Erlang. Our first major difficulty here was in understanding the WAM, since at the time there were no easily understandable description of the WAM. No things are better. The turning point came after having read chapter 11 of MA88, whose lucid description of a WAM-like machine gave us enough understanding to make our own machine. A compiler from Erlang to our own machine, called the JAM, and an emulator for the JAM machine were written. Initially, both the compiler and the emulator were written in Prolog. The resulting machine was blindingly slow. 5 Erlang reduction per second, 0.5 Erlang reduction per second when tracing the instruction, but served to debug the instruction set and work out the structure of the call frames. The primary advantage was that we could use Prolog's underlying memory management to write the emulator. Having worked out the instruction set and the architecture of the machine, the compiler was rewritten in Erlang itself on the emulator in C. This version, after 3 total rewrites, now runs 70 times faster than the original Prolog interpreter. A more detailed description of the implementation of the language can be found in AR91, where details of the JAM the instruction register on used in the virtual machine and the implementation of concurrency can be found. AR91. Which one? Implementation of functional programming. I think this is the next one I will read, I guess. Maybe not. Maybe this one is not present in the list. Okay, current status. Erlang is a well-established language for writing real-time software. 3 complete implementations exist, one in Prolog, the other 2 are standalone WAM-like implementation. At the time of writing, Erlang is in use at some 30 seats and is spreading at a rate of about 1-2 seats per month. It has been used for a number of prototypes on a small number of internal projects. The language is freely available for non-commercial use. Whoa, really? Really? So in 1992, this language was freely available. That's just crazy. So we were able to play with Erlang in 1992 without paying any bucks, just sending an email and having a version? Crazy. The development of Erlang language and operating system is part of the ongoing research program of the LMTEL Computer Science Laboratory. We would like to thank the head of the CSL, Bjorn Doker, for his help and support throughout the project. We would also like to thank all our users who have made developing the language so much fun, who have suggested valuable improvement to the language, and who have stoically accepted all our non-backward compatible changes to the language. 70 page and it's done. What kind of conclusion I can say here? I will just do a really short summary. This paper is great, really great, because we can see the evolution of the prototype to the final language. And the other great part is the old code coming from the past, 30 years ago. It's just working well, so you can just copy paste it and play with it. I think we have only one typo in the codes, and this one here, and the code is working. So that means at this time, if you were able to just copy paste this text, you were able to reproduce everything like I did today. So 30 years after these papers was published, that's when I'm talking about stability, consistency, and portability. In the past I was talking about C, but even C is not really easy to port everywhere. To be honest with you, when you have the wrong compiler, you can have a lot of weird behaviors. In this case, in Erlang, I feel like this is a really true portable language. I don't even know if Java, for example, like the one from the 90s, is still compatible with the last version of Java. I would like to test that. I think I will do a special live about that, because it's amazed me to see that. If you have a code running in the 90s, and if you just followed those kind of principles, there is a lot of chance that it will work today. Yeah, you will modify. need to modify some line of codes, probably need to check some parts of the modules and so on. But in fine, it will work. That's just crazy. So anyway, I don't really know if you bought something. I was so happy to read this paper. So there is no messages on YouTube or Twitch, and I think there is no messages on Discord, so no. Anyway, so it's over. Thank you to be there, and I hope you will enjoy this reading. That was not really easy. I think 1 hour and 30 minutes of reading is quite long, but we did a lot of tests, and I think you have everything to. If you're interested, just find this paper from your search engine. Sorry, a bit tired today, and just read it again and try what I'm doing. Just install SWI Prolog or any kind of Prolog interpreter, like I don't know. I think you have YAPL or YAM, something like that, and just try that. It's just working. It's incredible. It's just incredible. For example, if you take a look on Rust, Go, perhaps even Elixir, those languages, if you are using a wrong version, will probably not work with the recent one. For example, if you have modules and you want to use it from the past, I don't think it will work like that. To be honest with you, I never tried, but it should be interesting to try that. I think with Erlang you have one proof. This language was made to stay and be designed to be used in the future. Yeah. So anyway, have a good day, great weekend, take care of you, and see you for the next live session. Bye guys.